So the last talk was kind of a fluffy, thinking about how we program talk. This is going to be a more hardcore technical talk about where Java is going. I'm going to talk fast because I like to talk fast, and there's a lot to talk about. So the cool thing with this talk is I get to talk about the things that I'm actually working on day to day, which is, exciting, but it means it's a work in progress, and, could be all wrong. So since it could be all wrong, standard legal disclaimer slide. So, okay, let's talk about how we evolve the Java platform. There'll be a copy uploaded. So Java's been around for a long time, almost 25 years. And in those 25 years, it's been declared dead more times than I can count, and yet Java is still a very popular way for people to program, and we want that to remain true for the next 20 plus years as well. So how do we do that? From my perspective, the way to do that is stay relevant. Stay relevant to the problems people want to solve, stay relevant to the hardware people are running on, and keep our promises. Java code that was written 20 years ago still compiles, still runs without recompilation, and that's a good thing. And there's a lot of work that goes into making that so, but you only get one chance to break your promises to your users before they don't trust you anymore. So in the last couple of years, I think we've really accelerated the rate at which the Java language and platform is evolving. We've taken an approach of co-evolving the language and the JVM, and I think that's been a really successful approach for us. When I talk about keeping our promises, for the most part, I'm talking about maintaining compatibility. Java is successful in no small part because the code that you wrote 20 years ago just works. And, the cost of this is it takes longer. It takes longer to evolve the platform because we don't get to just go and break things. Moving fast and breaking things is not one of our values. But if you look at what that gets you, even though it takes a little bit longer, you'll see there's a lot of benefit. And a good example is what we did with generics back in 2004. So when we introduced generics, we gave users a choice. We said, you can migrate your code to use generics now, later, or never. You can migrate one class and not migrate another. At the boundary between generic code and non-generic code, you get graceful degradation. There's no flag day that says everybody has to recompile their code today in order for things to keep working. And this was, a pretty amazing thing because it allowed evolution to not be disruptive. It was also an expensive thing, and it's one of the reasons why it took a long time to add generics to Java. And you could tell the same story about lambdas. So it certainly took a long time for Java to get lambdas. But one of the things that we did that sort of maybe no one notices because it just works is code that was written, libraries that were written 20 years before Java had lambdas just worked with lambdas on day one without recompilation because we leaned on idioms in the language like functional interfaces rather than radically changing the Java type system to have structural function types. And so this is, this is a trick that we like to play, as often as we can. It takes a long time to evolve things in a way that look like it was just there from the beginning, but that's what enables us to build a stable enough base to build the next iteration on. And it's important to keep that in mind because language features are forever. Once you release a language feature, people are going to use that language feature in their code, and you don't get to change it. And language features interact with each other. They interact with other features, they interact with future features, and every language feature you pick to add to the language now is an implicit decision of 1,000 other features that you're never going to do. There's no shortage of feature ideas that people suggest to me in every medium imaginable of, you should add this to Java. And, the first thing I think when I see a new idea, well, no, I can't say that because I don't see any new ideas. I see a lot of ideas that I've seen a lot of times before. The first thing I would think if someone proposed a new idea is, okay, which of the 1,000 potential things that we're thinking of doing does this interact with? Because that's where all the complexity is. And that means if we don't know what the right answer is for something, we know we want to have something in this space, but we don't know what it is, the right thing to do is to do nothing. And generics were a good example of this. In 1995, we knew that Java wanted generics. It's not like parametric polymorphism was unknown at the time. It's not like we liked the idea that collections were dynamically typed. but we didn't know how to do it. And if we had done it in 1995, if some product manager had said, you have to have generics before Java ships, what would we have gotten? We probably would have gotten something like C++ templates. Is that the generics we wanted in Java? I don't think so. So we were willing to wait until we had a sufficiently Java-like solution, and we were pretty happy with where we landed. So, it takes a long time, but I think the result is worth it. But it's worth keeping our eye on the big goal about why we do language evolution, which is make it easier to build and maintain reliable programs. That's really what it's all about. Language features are cool, they're fun, but they're not what the customer wants. The customer wants a solution to their problem. They're a means to an end, and we just want to make it easier to build and maintain reliable programs. So I keep using this word evolve, and that's because I think that's really what's going on. Programming languages exist in an ecosystem, and when the ecosystem changes, either you have to evolve or you're going to die out. And I think it's obvious there's no perfect programming language, because even if there was, the sorts of problems that we want to solve with programs change over time, and if the problem is changing, what was the perfect solution for yesterday's environment is not going to be the perfect solution for today's environment. So, the way I think about it is, you have this ecosystem, and programming languages and tools, you can think of them as the predators. Programming problems, you can think of them as the food supply. And then there's an environment. We exist in this environment. It conditions what works and what doesn't. And rather than talk about, is a language good or bad, I like to think about whether a language is evolutionarily fit for its environment. Because that's what usefulness is for a programming language, that it's actually relevant to solving the kind of problems that we want to solve. And some creatures that are evolutionarily fit for one environment, they manage to adapt, and others don't, and they die out. Developer expectations change too. And this is also part of the ecosystem we operate in. So, Java 1.0 didn't have generics, and a lot of us grew to like Java even back in those days. But if you look back at code from 1996, and you think, my God, how did I live like that? Right? So at the time, I thought Java was incredibly cool, and it was at the time. But if it hadn't evolved, it would be substantially less cool. So, okay, so we're not done. Great, that means I get to stay employed. I like that. So there's lots of things we could do, but we have to keep our eye on the ball, and the ball is stay relevant, adapt to the problems people want to solve, adapt to the hardware people want to run on, adapt to changing developer expectations. And we're probably never going to be done, but there's a risk that the language can get full, and which is to say starts to collapse under its own weight. A good example of that is what happened with Perl. There will never be a Perl 6 because they hit their complexity ceiling, added so many things in Perl 5 that they just had nowhere to go. So we have to pick and choose our features very carefully. So, okay, so where have things been recently? Recently, about 18 months ago, we adopted a new release cadence. You've probably read about this. We've actually delivered 3 releases under this plan, where we're delivering releases every 6 months now. It used to be that our releases were feature boxed, and they were planned for like 2 years, 3 years, and ended up being more like 4 years because reality happens. This didn't work very well. It was difficult to accurately plan. The perception was Java moves really slowly. We didn't even want to do small features because they had a tendency to get stuck behind the big features. And there was a significant overhead for release management, because if the next train's not leaving for 44 years, you really want to be sure that everything that's supposed to be on the train is on the train. And as a result, the amount of time I spent in release management meetings was, well, more than I wanted to spend in it. And so by moving to a time box cadence, we can late bind features to ship when they're ready, and it's okay to miss the train because the thing's not done. Gets on the train when it's done. And the good news of this is I now spend no time in release planning meetings. I get to spend all my time on engineering. Well, not all my time, but the amount of time I lose to release planning has pretty much gone to zero. So this has been really successful for us. And if you look at the release history, you know, we've released on time the last 3 releases. So Java 9 came out in September 2017. It had roughly 90 JEPs. JEPs is our unit of our features. It's our planning process, JDK enhancement proposal. Java 10 came out in March 2018, 6 months later. Java 11, 6 months after that. Java 12, 6 months after that. These are obviously much smaller releases. Java 10 was only 12 JEPs, but it was only 6 months, not 4 years. And so what hasn't changed is the rate of innovation. What has changed is the rate of innovation delivery. And so this has also sort of enabled us to sort of change the way we plan features, which is nice. It's encouraged us to do smaller features, which I think has been really successful. So this has been a real successful shift for us. So, all right, so where have we been recently? So how many people here are running on Java 10 yet? 10, 11, 12? Some of you, most of you are still on 8? Right, okay. So even though this is 3 versions old, it's still new to most of you. So the language feature we added in Java 10 was local variable type inference. This is a feature that if you've programmed in Scala or Kotlin or any number of other languages you're already used to, which is to say, I want to be able to infer the type of a local variable from its initializer. So instead of having the exact type declared as the first thing on your line, URL connection, you can just say var name equal initializer. And you know, this is, it's kind of interesting. This was, you know, a really commonly requested feature. And then when we said we were going to do it, people were annoyed at us. Can't win, right? But, you know, we look at this as an option. You have the option, but not the obligation, to elide the type information if you want. And when might you want to do that? You would want to do that when it makes your program more readable. Which of these identifiers, the type or the variable name, is more important in your program? Usually, if you've picked good variable names, we all pick good variable names, right? That's what we do. If you've picked good variable names, the variable name captures more information about what this thing does in your program. And so that often, not always, but often carries more information than the type. And this brings the variable name sort of closer to the user's attention. And if you don't think it makes your program more readable, don't use it. This is a tool. It's not a requirement. It's not a fashion statement. So this is just for local variables. It's not for method return types or for fields. Pet peeve of mine, it's not just syntactic sugar. If I had $1 for every time someone said, oh, this is just syntactic sugar, I could retire. But it's not syntactic sugar because it interacts with the type system. You know, it infers the type of the variable from the type of the initializer. It's not dynamic typing. And the reason I say it's important that it's not syntactic sugar is the Java type system is more complicated than most people give it credit for. It has some weird types in it. It has intersection types, which you can't write them down, but you can use them. It has capture types, it has anonymous class types, and these get some special treatment. So for example, if you say var c equal this.get class, you would think that that would infer type class of question mark, but it actually infers a capture type. It infers the capture of question mark at this particular use of the code. And similarly, if you say, oops, what happened there? Var numbers equal list of 1, 2, the string 3, you would think that might give you list of object, but in fact it gives you list of question, extend, serializable, and comparable, and it's actually an infinite type that gets truncated at 3 levels of depth. And this is something that mostly was only of interest to compiler writers, but now that you're asking, I want you to infer the exact type the compiler knows about at this point in the program, they will be exposed to you. So, double-edged sword, convenience, but now you are exposed to the complexities of the Java type system a little bit more. Like I said, this was the most commonly requested feature that we got. And then when we said we were doing it, there was all this angst about it. They're like, you're just enabling bad developers to write bad code. You know, like there's anything we could do about bad developers writing bad code, right? You're just giving into fashion. You're just copying from, we heard it all. And what was funny about it is that sort of we heard this crescendo of doom about, you know, how you're going to ruin Java and this is the worst thing you could possibly do. And then we shipped and nobody said anything. because the controversy was over. It was happening. There was no way they could stop it. People got on with their jobs. And people seem to like it. It's going to take some time for people to get used to it. It's going to take a little bit of time to figure out how to use it well. So we've published a frequently asked questions and a style guide that I think will help people learn when to use it and when they shouldn't. And this is something we'll continue to do for new features going forward. Okay, so what's coming up? So as we've moved to this rapid cadence, we've decided that maybe it's a little too rapid, and we want to give features a chance to be provisional for 6 months before they become permanent. So we have this notion called preview features. When a new feature comes out, it goes into preview status for 6 months. For preview features, you have to opt into them. It doesn't mean they're experimental or half-baked. They're complete, fully specified with IDE support and all of that, but it's largely an opportunity for us to gather broader support and feedback from the community while we still have a chance to make some changes. And the idea is that a preview feature either will graduate to permanent status in the next version, or maybe it'll get some changes and it'll preview again, or maybe in the absolute worst case, it was a disaster, we're gonna pull the plug and we're gonna yank it. So don't use them in production, but you should pay attention to the preview features that are coming, because this is your sort of last chance to have feedback before they become permanent. So like I said, you have to opt into them so people don't accidentally use them, so people don't put jars with preview features in Maven Central and have people accidentally being dependent on them. We don't want that to happen. But like the IDEs now all have support for it. I don't know if you can see this, but when you pull up the project language level in IntelliJ, it gives you options for 12 or 12 with preview features enabled. So that's pretty cool. Okay, so that's mechanism. What's actually using this? In Java 12, we have a preview feature which are enhancements to the switch construct. Switch is kind of an unfortunate story in Java. It was borrowed very heavily from C. You could almost see the C spec. Like, if the paper of the Java spec were thin enough, you could see the C spec underneath it, for the specification of Switch. And in reality, the way people use Switch is really not the way that the language feature was sort of imagined. And so there's this friction. It's really common, for example, for people to use switch statements as if they were expressions. And in every arm of the switch, every case, you're assigning to some local variable. And it's kind of a roundabout way to do a multi-way expression. And the thing everyone hates about switch is break, right? You have to break Y is fall through the default rather than the exceptional case. And thank you C specification for that bit of inheritance. So we started looking at the problems of the switch statement as we looked at a bigger feature, which is pattern matching, and I'll talk about that in a few minutes. And then we realized, well, a bunch of these enhancements that we've done to switch as part of this bigger thing, they can stand on their own. So we're going to let them settle out as their own little feature, and we're going to preview that in 12. And the two improvements to switch we have in 12 are switch can be an expression, and there's a streamlined form that does away with fall through for the most common cases. So let's look at what's wrong with switch. So here's a typical switch statement that is simulating an expression. There's a lot of repetition here. So in each arm, we're doing an assignment to a local variable, and we're hoping that we do that in every arm, because if we skip one, we have a bug. And then you have these annoying breaks, which are pure ceremony. And then, to add insult to injury, even though you're switching over an enum and there's only 7 days in the week, you have to have a what do I do if it's the 8th day of the week? And, and what does the code there do? Well, it's always going to throw, right? It's so it's just annoying code that you have to write that you hope never gets executed. So here's how this code should look, which is to say switch is an expression that yields a number. And you can say for multiple cases, if it's Monday, Friday, or Sunday, then it's 6 letters. If it's Tuesday, it's 7 letters, etc. And because I'm switching over an enum, and the compiler has validated that I've covered all the cases, I shouldn't have to say default. The compiler is still going to insert a default for me, just in case at runtime your enum acquires an 8th value. And what does that default do? It's going to do the same thing you would have written by hand anyway, so why make you write it out? Okay, so this is using both of the new features of switch as an expression, and also the streamlined form of case labels, which is single consequence cases. So case, value, arrow, expression, which covers about 95% of the way people use switch. So these are two orthogonal enhancements. One is it can be an expression, it can be a statement, and the other is you can use the streamlined form of labels with a single consequence, and you can use those in switch statements as well as switch expressions. And so if you have a single consequence, the concept of fall through doesn't even make sense. We let you put multiple labels on one line because why wouldn't we? And you very rarely need to use break. And like I said, you can mix and match these. We expect that what's going to happen is the most common configuration is going to be expression switch with the new label form, but people can use it however makes sense in their programs. So okay, so that's cool. That's in Java 12, which is no longer even the current release, right? No, Java 12 is the current release. Yes, I can't even keep it straight. That's how fast we're moving. It's wonderful. Okay, so what's coming up? We've got a couple of projects that are going on inside OpenJDK that are evolving the platform. Amber, Valhalla, Panama, Loom. I'm going to talk about two of them. I'm going to talk about Amber and Valhalla today. The Project Amber is largely, you can think of it as right-sizing language ceremony. All the features that kind of annoy people about how much code they have to type, can we up-level the level of, the level of expressiveness of the language? These are very often the kind of smaller features that we would not have done under the old Cadence when we were focused on big things like lambdas and modules and generics, but they're things that make a difference for people's everyday programming anyway. So a couple of features that we're working on. The biggest one is pattern matching. If you've programmed in functional languages, you're familiar with pattern matching. If you've programmed in other object-oriented languages, you're starting to see this show up in other languages like C#. And the basic idea behind pattern matching is there's these three things that we do all the time when we write programs. We test something, and then we do a conditional extraction. If you are one of those things, let me get some property, and then we bind them to variables, right? So a really simple example is an instance of test. If object instance of integer, cast it to integer, that's a conditional extraction, and then bind that to a local variable, and then use that local variable in the rest of our program. And since we use this pattern over and over and over again, it makes sense if the language makes that easier to express. And like one of the most irritating things about it is I have to repeat myself here. I have to say instance of and then cast. What else could I possibly do after I do an instance of test other than cast? Well, there is one thing I could do. I could cast it to the wrong type because I cut and pasted from somewhere else. So it's sort of like the language daring you to make a mistake. Go ahead, cast that to the wrong thing. I dare you, right? So this isn't really helping you write better code. And it gets in the way, right? The half of the ink on this page is the cast, which you don't even want. So there's a lot, in the category of things people suggest, people say, oh, we'll just use flow typing and that would solve the problem. And yes, flow typing would solve the problem in a very limited way. There's a much better way to solve the problem, which is pattern matching. And what a pattern does is it fuses these three things, a test, a conditional extraction, and a binding into one language construct. So here's what this code looks like using a type pattern. A type pattern looks like a variable declaration. You have a type name and an identifier. And it's not an accident that it looks like a variable declaration. And you can put a type pattern, or any pattern, on the right-hand side of instance of. So you say, if object instance of integer and then name, and what that will do is it'll do all three things at once. It'll do the test. If the test passes, it will cast it to the appropriate type, and it will bind the cast value to that name. And then you can just use that name, right? So 100% of the casts in Java code could just go away. That's kind of cool. This is just scratching the surface of what pattern matching does. And there are other places we can use pattern matching as well. It works very nicely in switch statements. The first place it's going to show up is instance of, and then we will broaden from there. it interacts pretty nicely with the short-circuiting Boolean operators. So as an example, think about the code you've written, or more likely that your IDE wrote for you, for the object.equals method, where the first thing you do is an instance of test, and then you do a cast, and then you do some complex stateful logic with nasty control flow to try to micro-optimize all the cases that you shouldn't be thinking about. And no human can actually follow that without actually pointing their finger at the screen. With a pattern match, you can write this as one expression where you say return object instance of whatever class and bind it to t, and his size is equal to my size and his name is equal to my name, and the variable t is in scope in these later clauses if and only if the instance of succeeds, and the compiler will check that for you. So this is a much more natural way to write something that we've been writing in a kind of unnatural way until now. Let's take a look at how this works in a switch statement. So phase 1 will be patterns in instance of, phase 2 will be patterns in switches. So here's some typical code that you write where you're casing over some dynamically typed object, where all you have is an object, you don't know what it is, so you have to say, are you an integer? Okay, cast it to integer. Are you a long? Okay, cast it to a long. And repetition everywhere, right? So repeating the test and the cast, repeating all the tests, repeating all the assignments, it's not pretty. So I can rewrite this switch using type patterns. My case labels just become type patterns. Instead of saying, if x instance of integer, I say case integer I. And what that means is my switch target an integer? If so, cast it to integer, bind the result to I, and then I is in scope for the control flow that's dominated by that case. And I can actually reuse I in other cases if the control flow is, is cooperative. So this is already better than the previous code, right? So the previous code was like this. The casting, kind of obfuscates what's really going on. This code is already getting easier to read because the business logic is sort of more front and center, but of course we can do better. This switch is morally an expression. We'd like to be able to write it as an expression rather than as a bunch of statements, which with expression switches we can do. So now I can express that whole previous page of code, which gave me 5 places to make a cut and paste error, with this much simpler code that is kind of the code you had in your head when you sat down to write the thing 2 pages ago, right? So, not rocket science, but making it easier to build and maintain reliable programs by removing places that bugs hide. Repetition is a place for bugs to hide. So it's not, we dislike repetition not because that means more typing. I don't care how much typing I have to do. I care about, is my code readable? Is my code maintainable? Is it free from obvious errors? And repetition is where bugs hide. So take away the repetition, take away the places for bugs to hide. So, okay, that's pretty cool. What else are we working on? So one of the other places where there's a lot of error-prone repetition in Java code is when you're modeling data. So if you want to write a class to model some data, a person as a first name and a last name and an age and an address, etc., that's a lot of code you have to write. And we all know how to do it, and we all know how to make the IDE do it. But the way I describe this is the modeling overhead is high. I have in my mind, I want a thing with a name and an age and an address, and that's all I want. In my head, that's all there is to this class. But the amount of code I have to write to express that very simple concept is too much, so it's tedious while the IDE automates that. It's error-prone. You have to look at all that code to conclude, I didn't have to look at this code, right? That's not what people want to do. You want the code that's there to do something. Right? You don't, if the code is obvious, you shouldn't have to look at it. It's only the non-obvious code that we want to have to write down. So things like constructors and accessors and the object methods is all boilerplate. And my claim is the reason we end up needing this boilerplate is that we're writing at the wrong level of abstraction. We're trying to model things as objects when really this stuff is just data. So if we had a way to express this class is just a carrier for its data, that's it, nothing magic here, then we've given up something by doing that. We've given up some flexibility. We've kind of constrained the API of our class to match the shape of our data. In exchange for having given that up, the compiler can give us free code. So sometimes that's a great trade, right? And it's a little bit like enums. Enums are one of my favorite features in Java, even though I don't use them very often. And about a typical code base, enums are like 3 or 4% of the classes. But enums are great because they represent a very sensible trade where the programmer says, I'm willing to give up control over instances to the runtime. And in return for that, giving up that control, the compiler says, oh, okay, if you're willing to give up that, I can automate this and that and the other thing for you. I can give you an equals, and I can ensure that they're interned and all of that. And when that trade is a good deal, you're happy to take it. So let's make that same deal with data modeling classes. So, this is the code we have kind of in our head. This is the code that we have to write. And so let's write it like this. Okay, now this is not magic. We've seen this in other languages. Scala has case classes. There's lots of languages that have optimized forms for data modeling. But the design center here, from our perspective, is this isn't about boilerplate reduction. Boilerplate reduction is an ancillary benefit. What this is really about is better semantics. I'm saying that a point is, full stop, an x and a y. Its construction protocol, its deconstruction protocol, its equality protocol are derived from that xy. And that means I can reason about points more easily than I can reason about classes whose bodies are just arbitrary bags of stateful logic. So not every class that we write is going to be a record, just like not every class we write today is an enum. But for the classes that are, it makes it easier to reason about them. So, like I said, they make this semantic statement. I'm just a carrier for my data, and in return, we get some boilerplate reduction. We also get some benefits like, if you know that this class is just a carrier for its data, then you know how to freely deconstruct it and reconstruct it. That means things like serialization or marshalling to JSON can come mechanically for free. So that's the benefit of focusing on semantics rather than boilerplate. And like I said, it's the same trade we made with enums. That was a good deal, so let's play that trick again. So records give us actually half of a construct that is known as algebraic data types. You probably haven't seen the term algebraic data types. It shows up more in functional languages. But records are what's called a product type because the state space of a record is the Cartesian product of the state space of its fields. So if I have a point with x and y, then the state space of point is integer Cartesian product with integer. So they're called product types. The other half of algebraic data types are called sum types, and those are discriminated unions, and they turn out to be fairly useful as well. A sum type is basically saying, an x is either a y or a z. Doesn't have to be two things, it can be many things. But that is useful because it allows you to reason about exhaustiveness. So if I say a shape is a circle or a rectangle, and then I am switching over the kinds of shapes, if I've covered circle and I've covered rectangle, I don't have to say default because I've covered all the cases, just like enums. And it turns out that sum types and product types tend to travel together, or they travel very well together, that by defining things as sums of products, you're able to say that a shape is a circle or a rectangle. A circle has its state is a center point and a radius. A rectangle, its representation is, let's say, it's 2 points. So each one of them has a strongly typed definition, and then we say shape is the union of those things, and I know that it's either a circle with a center and a radius, or it's a rectangle with 2 points. And this is how we would write that. So this is pleasingly compact. I have the record I had before with point. A point is just an XY pair. And then I say I have an interface shape, and I say it's sealed. Sealed means it's a little bit like final. Final means I can't have any subclasses. Sealed means I can only have a specific set of subclasses. So I get to control who my subclasses are. And in particular, the subclasses of shape are, in this example, are circle and rectangle. And a circle is a record which has a center point and a radius, and a rectangle is a record that has a lower left and an upper right boundary, and that's what a shape is. So nice compact definition. You could use this anytime. How many people here use the visitor pattern? Anytime you use a visitor pattern, this is really what you want. And you can, anytime that you're using the visitor pattern, you can dispatch over it using pattern matching much more compactly and directly and flexibly. So records and seal types go well together, and records and pattern matching go well together. So one of the things about records is they're transparent. I can take them apart. I can take a point and say, give me your X and Y. And so I can define a kind of pattern that describes that deconstruction. We'll call it a deconstruction pattern. You can think of it as being the opposite of a constructor. So what does a constructor do? It takes some state elements and gives you an aggregate back. What is deconstruction? It takes an aggregate and it gives you the state elements. And hopefully you've written it in such a way that if you deconstruct it and then you pass those things back to the constructor, you get back something that was equal to the first thing you started with. If you write your equals wrong, then you won't get that. But so a deconstruction pattern is a fancier kind of pattern. We saw type test patterns. Here's an example of a deconstruction pattern. Circle, that's a type. And then I have some what look like variable declarations, but are actually nested patterns, where I say, if shape instance of circle, var center, var radius, the pattern is fusing three things. A test. The test is an instance of test. Are you a circle? If you are a circle, cast it to circle, extract the center, extract the radius using getters or something like that, and bind them to local variables that I can use inside the body of that if block. Okay. Now, you could certainly write this without pattern matching, and you can imagine how many lines of error-prone garbage you would have to write. And when things get nested, if you have, a rectangle whose lower left is a point and the point has x, y, now you have two layers of casting and binding, and you can barely see your business logic for all the garbage, right? So this does away with that, and it actually nests and composes fairly nicely. So this is, think of this as phase 3 of pattern matching. Again, we have this rapid cadence. We can divide features into smaller bits, where once we have records, you'll be able to decompose records using pattern matching, and you'll be able to write deconstructors for ordinary classes. They're just code, like a constructor, except they work in reverse. And there's no magic here. It's not like we're magically guessing what the center is by looking at field names. I'm invoking a member of the class, which is like an anti-constructor. And if you declare records, you get these deconstructors for free. So let's look at how this would work. I want to compute the area of a shape. I know a shape is a circle or a rectangle. I know the area of a circle is pi r squared. I know the area of a rectangle is delta y, delta x. So I switch over my shape. I say, are you a circle? If so, extract the center and the radius. I didn't even need the center, but I said it anyway. And yield as my area pi r squared. And if I'm a rectangle, extract the lower left and upper right coordinates as points, and compute out delta x and delta y and multiply them together and return that. And do I have to have a default case? No, because I'm switching exhaustively over a sealed type, so I don't have to say the default. That's kind of nice, right? Now, if you didn't have this, you would go visitor pattern. And visitor pattern is another one of those dancing bears, right? It's kind of cool, but it kind of sucks. And there's a conspiracy theory that says the feature that compiler writers always want to add to their language is pattern matching, because compilers are all pattern matching. And okay, we're a little bit guilty of that, but it's really darn useful. And once you have this, you're never going to want to program the old way. You're never going to want to use the visitor pattern again. Okay, so I'm going to switch gears. Those were the, quote, small features that we're working on. Let's talk about one of the big features we're working on. And we're really working on a lot of stuff here. I would say that a hidden side benefit of this rapid cadence is our feature pipeline is better than it's ever been. Because when we did a big release like 8, we delivered everything we were working on, and then the pipeline was empty when we started 9. And we're never going to be in that position again, I promise you. So Project Valhalla is aimed at adapting to the fact that computing hardware has changed so much in the last 25 years. And those of you who remember the first time I came to ETE about 5 years ago, we were just getting started with Project Valhalla then. You've probably been wondering, they've been talking about that for years. Where's that going? Well, we've been working on it. It's a hard problem. We knew it was a hard problem, and we're actually getting the upper hand on it. So in the last 25 years, hardware has changed an awful lot. It used to be that the relative cost of a arithmetic operation compared to a memory fetch was about the same. They reach a handful of cycles. Now, if you look at a modern processor, I can issue 4 arithmetic operations per cycle, but if I cache miss out to main memory, that's going to cost me 300 cycles. That's a factor of 1,000 difference in this one cost measure over the last 30 years. So it stands to reason that however we laid things out in memory 25 years ago is probably not optimal for today's hardware. Java's data structures tend to be very pointery. You have little small islands of data connected with pointers to other islands of data. And the reason for that is everything is an object. Objects have identity. The best way to implement object identity is with pointers. And identity is relevant to objects for polymorphism, for mutability, for locking. Not all objects use those things. My point object didn't use that thing. Why am I paying for it? So here's the data layout we have now. Let's say I have my class point, and I have an array of points. And what's an array? It's an object. It has an object header, and it has a bunch of pointers to hold references to objects. And each one of those pointers points to a full-blown object with an object header. And so if I look at memory density, let's say an object header is 2 words. So I'm looking at about 3 words of overhead for 2 words of data. That's not so good. And if I'm looking at a number of indirections, every time I traverse one of these pointers, I'm risking a cache miss. Because even if the array is nice, is all hot in cache, and the prefetcher is working to go pull the next chunk of the array into a cache line, all of those data items are going to be cold in cache, and we're taking cache miss every time. So the data layout we have gives us poor density and poor flatness. Now, sometimes that doesn't matter. Very often the performance is just fine. You don't need to do anything. Yeah, it's theoretically inefficient, but life is short. But sometimes developers will take it in their hands to try to fix this themselves, and they'll do this. They'll shred an array of points into an array of x's and an array of y's. How many people? I'm not going to ask anybody who's done this because you're going to lie. How many people here have seen other people do this? So yeah, and sometimes we do this out of genuine necessity, and sometimes we do it out of some misguided obsessive compulsive behavior. But the problem is we've just made our code less readable, less maintainable, and more error prone. And that's not good, right? That goes against the prime directive. Make it easier to build and maintain reliable programs. And so why do people program this way? It's because we gave them a bad choice. We said, you can have abstraction, you can have performance, pick one. And big surprise, programmers pick wrong when you give them that choice. Programmers are obsessed with performance even when they don't need to be. So unfortunately, just like we spent 30 years trying to figure out how to make compilers auto-parallelize calculations and we failed. We've spent probably a good 10 plus years trying to figure out how to make VMs do escape analysis, and we failed on that one too. So what we need is some help from the user to say, I don't care about the identity of this object. And if the programmer gives us that permission, then we can give them the layout that they actually want, which is an array of points is xy, xy, xy. We get nice, flat, dense use of memory. So the question is, what kind of code should people write to get this layout? That's the question we started with 5 years ago. Yes, we've made progress since then. Okay, and the answer is, we used to call them value classes. We're calling them inline classes now. The idea is you're saying, this is a special kind of class. I'm not going to use mutability. I'm not going to use representational polymorphism. And in return, I expect you to routinely inline the layout of this class into arrays and other objects. Pass it by value, shred it into fields and pass them in registers. Do what you want because it's just data. There's no identity here. And so, these are, you can think of them as pure data aggregates. They're just their data, no identity. You compare them, they're equal if their states are equal. And we give up a few things, like I said, mutability and representational polymorphism. And in exchange for what we give up, we get routine flattening into arrays, into other values, into objects. No object header is needed. And we basically get objects with the runtime behavior of primitives. So that's pretty cool. But unlike primitives, they have more stuff. They have methods, they have fields, they have generics, they have encapsulation. So you could think of them as sort of halfway between objects and primitives. They have, you can think of them as faster objects. You can think of them as user-definable primitives. And which one is it? Well, the answer is both. Our mantra is codes like a class, works like an int. So who cares? My claim is everybody cares. If you're writing applications that process large data sets, you can fit more data in memory. You can access the data more efficiently and do computations faster. You can reason about locality and footprint in a way that you couldn't. So if you're doing machine learning, and we're all doing machine learning, right? We're all going to be replaced by machine learning. This is really relevant. If you're writing libraries, like I do, how many people here would like HashMap to be faster? Right? If we can make HashMap faster, every Java program gets faster. Well, what do HashMaps have? They have a lot of indirections. We can squeeze out some of those indirections by using values. We can make classes like optional into values, so you don't have to allocate a node on the heap to return something with an optional. So we can make the libraries that you use today more efficient. Compiler writers love this. Let's say you're writing the JRuby compiler. JRuby's numerics aren't the same as Java's numerics. They're not fixed 32 and 64 bits. They overflow. So you have to model them as objects, which sucks because 99.9% of the time they don't overflow, but you have to model everything with an object anyway. If you can model it with a value that doesn't take an indirection, doesn't have an object header that you can pass through registers, JRuby numerics will get 12 times faster overnight. That's a cool thing. So even if you're not going to use these directly, you'll be using them indirectly through your compiler, through your library, and your programs will just get faster. So we've been doing this. I'm probably running out of time, so I'm going to talk a little faster. We've been doing this almost 5 years. In that time, we've built 5 rounds of prototypes, each of which was aimed at a different aspect of the problem. And we are finally at a prototype that is usable by humans. Yay. Should be coming out actually in the next few months or so. It's actually quite solid at this point. So if any of you are doing data structure experimentation or anything like that, it's something that you could download and try out. And to give you an idea of the kind of performance benefits you can expect, we took a sort of painfully parallel example, which is multiplying matrices of complex numbers. So how do you do that in Java? Well, there's no primitive for complex, so you write a class. And it's got a real and an imaginary component. And how do you add 2 complexes? Well, you add their reals and their imaginaries, and you wrap them with a new object. And off to the allocator you go. And how do you multiply them? Same thing. And when you multiply matrices, how do you do that? Well, you allocate big arrays of them. So this code is really easy to write, and it's really easy to read, and it's really easy to be confident that it's correct, because you look at the complex numbers textbook, and you look at the code, and they're almost the same thing. But there's all this allocation going on the side, which kind of sucks. And so we took this program, ran it for some big matrices, and we took the regular version, and then the version where you put inline in front of class complex. That was the only change. And what we got was a factor of 12x in performance improvement. That's cool. Factor of 1,000x in allocation reduction. All right, so we picked an example that was really easy to beat up on, but this is pretty significant. And more interestingly, remember I was talking about modern CPUs can issue 4 arithmetic operations per cycle. So when we ran the benchmarks for this, we had it look into the CPU performance counters to tell us how many instructions were being retired and how many cycles did it take to execute the program. And in the boxed version, we were getting on the average of 1 instruction issued per cycle. In the value version, we were getting almost 3, because by eliminating all this memory data movement and all the times that the CPU has to wait for the memory subsystem to cough up some numbers to be multiplied, instead we could actually be doing actual work. And so we went from using a quarter of the theoretical capacity of the processor to almost three quarters, which is a pretty big difference. So this stuff is starting to get real. It's really cool. And if you're, like I said, if you're into algorithms, you might want to check it out. So, okay, summing up, our pipeline is better than it's ever been. There's features coming from Project Amber that make everyday programming more pleasant, and there's more features coming: record, seals type, pattern matching. Valhalla, after years, is starting to bear fruit, and we're getting solid results with real code, and should have early access builds in the next year. And 2 projects that I didn't talk about, Panama, which is about native interop, and Loom, which is about coroutines and fibers, are also making huge progress. So it's a really exciting time to be working on Java. I hope it's a exciting time to be working with Java. And if you come back next year, you can gauge how much progress we've made since this year. So thank you very much. And do we have time for questions? We should, right? We have 8 minutes for questions. Okay, great. So let's... Okay, so I'm going through the questions on Slido. So first question, sealed types. What is the set of possible subclasses of a sealed type? So that's a great question. There's 2 options. There's an easy option, which is if they're all declared in the same file, we infer them as the set of classes declared in this file. Or if you don't want to declare them in the same file, you can have a list. Sealed interface foo permits A, B, C, D, and then that will be an exhaustive list of the permitted subtypes. Have I seen any features in other JVM or non-JVM languages that you'd like to add? Oh my God, yes. So I want Java destructuring. Is there a possibility for it to show up as a preview feature? Yes, destructuring, like I said, will be built in to records, which we'll likely preview in the next year. And sometime shortly thereafter, you'll be able to write destructuring patterns for arbitrary classes. Can records be made immutable? In fact, they cannot be made mutable. Records are immutable. They are transparent carriers for shallowly immutable data. Let's see. How do you differentiate good features ideas from the trendy ones that may go extinct? That's a really good question. So the touchstone that I've repeated like numerous times in today's talk is, does this make it easier to build and maintain reliable programs? And I don't care how much effort it is to type the program text out. Writing code isn't important. Reading code is important. So does this feature make the semantics of the program pop out of the page to the reader? Because if the program is crystal clear about what it does, then it can be maintained. If the program is confusing or tricky or clever, then someone's going to try to maintain it, they're going to break it, and they're going to say, we have to throw out this old code and rewrite it. And that's value destroying. We want to preserve the value of the investment you've made in your code, and we look at things as, does this help users preserve their investment? And so that's the lens we look through. That's can we get rid of semicolons? Can we please stop asking this question? So this is a good example of a question that's not even worth wasting breath on, except that I get asked all the time. The amount of work it takes to make a change like that is enormous. the actual value is 0. In fact, the value is negative, because when you go from a language that uses semicolons to good news, everybody, semicolons are optional, we now go through a transition period where people are focused on removing semicolons from perfectly good working code, rather than focused on writing new code or fixing bugs in old code or doing something that actually adds value. So trivial syntax features like semicolons are so deeply value destroying to even talk about that I'm going to go on to the next question. Can we have inline records? Yes, great question, thank you, I'm glad somebody asked that. So you might say, this records thing is about data, this inline thing is about data, why aren't they the same feature and do they work nicely together? They actually aren't the same feature, but they do work nicely together. So records are about, does my API match my representation? Inline is about, is my identity semantically meaningful? And for each of these things you're willing to give up, you'll get a benefit. Are there cases when you're willing to give both up? Yes. If you give up both things, do you get both sets of benefits? Yes. So a lot of records can be inline records, and they will get the memory layout benefits as well as the API benefits. How many languages am I fluent in? Define fluent. As an architect, I spend more time in email and PowerPoint than I do coding, so the answer might be 0. How many languages have I programmed with in my career? 20 plus. What do I program in when I'm not programming in Java? Usually Haskell. Am I a good Haskell programmer? Well, most Haskell programmers who look at my Haskell code say, this looks like it was written by a Lisp programmer. So you decide. Can the value being switched on be of different types? I think what that means is, can you switch on a really general type and case off of int and string and what have you? And the answer is yes, but asterisk. We're still not finished with the problem of primitives. So one of the things that's coming in Project Valhalla after we deal with value types is how do we do generics over value types? How do we do generics over primitives? How do we heal the rift between primitives and classes? All of those are on the board. We've spent several thousand hours thinking about those problems. They're very hard problems. We fully intend to solve those before I retire. Let's see. Things keep jumping when I try to scroll because people are asking new questions. So what is inlining in the context of compilation? That's actually a really good question. Inlining is not a compilation feature, it's a VM feature. So value types are one of the reasons value types are taking so long is they are pushed all the way down into the JVM and the bytecode set. So when a class gets loaded that's an inline class, the VM knows that it's an inline class. And when it does its layout computation of how do I lay this class out, it inlines the any contained inline types into the layout. So the awareness of inlining is pushed all the way down basically to the metal. Is there any equivalence of Scala's case classes on the horizon? Yes, that's records. Are the new preview language features compilable into bytecode that can run on older JVMs? No. That is a feature, not a bug. If you want to use the new features, run on the new JVM. And the reason for that is not only are there a lot of benefits that come from upgrading to the newer JVMs, like performance improvements and dealing better in Docker containers and all of that stuff, but there are often subtle dependencies between the code that's generated by the compiler and the runtime library, and sometimes the bytecode set. So our policy is new features require new JRE versions, and that's just how it is. But there are new versions coming out all the time, and with the delta between each version of Java getting smaller, the overhead of moving to the next version of Java is correspondingly less disruptive. Why did we choose positional destructuring over name-based? That's a good question, and it's also an easy one because everything else about invoking code in other classes is positional. So this is actually a much deeper question, which is people are constantly saying, But in this new feature, you could do it this other way. In fact, someone said to me just yesterday, well, like in the new switch expression, you could leave out the semicolons because there's no compatibility consequence there. And ignoring like the head shaking about the semicolons thing, the reason that's a stupid suggestion, the reason that's an unworkable suggestion, it's no stupid suggestions, is do you really want to program in a language where the semicolon rules are different for a switch expression than for a switch statement? Ugh, no one wants to program in that, right? Similarly, do you want to program in a world where you can use name-based invocation for red methods but not blue methods? No, no one wants to keep that in their head. Do we want to eventually get to name-based invocation? Maybe. When we do it, it'll be available everywhere. But we're not going to do it halfway. And we're not going to look at new features as vehicles for changing decisions that were made 25 years ago just because we can. A good example of that was when we did lambdas, people said, well, why don't you make the lambda parameters implicitly final? Because implicitly final is better. And one of the reasons why we didn't do that is that makes it harder to refactor between lambdas and inner classes. So yes, if we could have wound the clock back 25 years and made all parameters implicitly final, we would have done that. But to make only the red-colored parameters implicitly final, that's just mean. So we're not going to do that. So I think we're out of time. So thank you very much, everyone.